Hello friends, today I'm going to talk about Leetcode-473 matchsticks to square. The problem is given a number of matchsticks, you find out the way you can make one square by using up all those sticks. You should not break any stick, but you can link them up. Each matchstick must be used exactly one time. So assume that little match girl has this stick in this array. The element in this array represents the stick length. So here this is we have 5 sticks and the lengths are 1 1 2 2 2, so we can make a square with each side's length equal to 2 here. So the problem returns whether we can make one square, return true or false. Let me give another example here. If the little match girl has this matchsticks and we can make a square with each side has 1 2 3 sticks, right? So this problem that first we have find that each side has the same length. Secondly, we use all the sticks. From these 2 points, we can get the conclusion that we get the sum of this is all these sticks, and if sticks could be modulo by 4, if it could be modulo by 4, we can find we can make a square. If it's not, we cannot make a square. So the first case is whether it could be modulo by 4 here. Secondly, if it is, then we get the side length of the sums of all the sticks divided by 4 here. So then the problem is transfer to find 4 subsets, sum that equal to side length here. And we also have to find all the sticks and use all the sticks. So it's definitely that we can use a recursive way to traverse all those sticks, traverse all the sticks and recursively to find whether we can make up this or it could be used a dynamic program here because it returns true or false. And of course, use recursive is easier because it's intuitive and easy to program here. So here I'm going to talk about recursive here, and like this example here. And if we use a recursive way, it seems that we have to traverse this is 1 and 1, 1, 1 and 2, so we have to traverse then 2, 2 again, 2, then 2, and 2 for each subset. So we can define a subset for that. For each subset, we have to find the sum that is equal to this sublength here. So actually, we are going to find then etc. here, like here, and here, something like that. So actually, we have to find the subset is not this subset, and for every one subset, and for another subset, we also when we traverse here, for example, traverse here, etc. and 3 here, and we also need to find this subset. So we can use this recursive, or actually it's a backtracking technique. When we traverse this backtracking technique, we can find the subset here. So for each way in this sets, and we have to when we traverse, we have to get the subset plus the current numbers, the current index numbers, and check whether the numbers is equal to sublength. If it's less than sublength, then we continue recursive call. Here, and so we have defined a help function here, and here we could recursive call the help function here. This is basically the idea of the recursive call. Of course, in this recursive call, then we have to define a base case here. Here that should be the base case. The base case should be that if the current index is equal to the current length, then we check whether the sets 0 and sets 1 and so sets 2 equal to sets 3 actually here, because we have make sure we have guaranteed that the sum of this num is equal. Can be made up by the square, so we just guaranteed all three equal third lengths, and the sets the last sets must be sum must be equal to third lengths. So here we have defined the sets for each set I is the sum of the subsets here. That should so in this way we just get the sum of each equal. So basically this is the idea of the backtracking and all the called DFS techniques here. Next we are going to write the code here. So we define a help function here, and we get the sets and also index and also the third length here, and we get the base case here. The base case is this index equal to if we have traversed the last element, we will check whether the sets 0 equal to sets 1 equal to sets 2 equal to third length. Then we have found the answer, we return true. Otherwise we return false here. So we recursively call for sets. For each set we check whether these sets are plus the kind of index values, whether this values, if this value is smaller, then we call for. So we have to add if sets are plus nums index smaller than third length, smaller or equal third length, then we update the sets are them and call recursively again. So we call this equal help function here. Nums sets is the same and index the plus 1 and third length is the same here. If this function return true here, that means the subproblem is also return true, so we return true here. If it's not, so we have to backtrack and reduce back. We have to delete the previous numbers from the sets from the kind sets sum. Then we return the false here. So basically this is a call function here. And other cases not nums or nums less than 4 here, and we return false. We get the third length equal to some nums So we first get the sadness. If current value is could be modulo by 4, so we need to for those. Then we here we update the sadness, and we define the sets here. For element here, then index equal to 0. Then we call this function here. We return here function here. Actually, here, if we sort these numbers first, it could dramatically reduce the time complexity, because every time we find the biggest length of sticks that we will encounter firstly, and also quickly to trim the trees fast. Then we start from the smallest numbers here. They trim tree earlier if there's no answers. So then we check this function here. Okay, true. And we check this function. Yeah, good. We made it.